I'd like to welcome you all to the third in our monthly series of composting webinars. This webinar is Composting Systems and Methods. The speaker today is Craig Coker. Craig has been in composting for 35, 40 years. He has years as a planning, permitting, design, construction, and operation, all of those. He's worked with animal manure, animal mortalities, food waste, biosolids, yard trimmings, anything else that's organic. Craig serves on the board of directors for the Virginia Recycling Center. He's the senior editor at Biocycle magazine. He's an engineer and a scientist and has experience in all forms of composting. So I'm going to turn this over to Craig, and I'll be in the background.
Thank you, Gary. Good afternoon, ladies and gentlemen, and thank you for joining us for the Composting Systems and Methods portion of the webinar series. Some of the content in this class has been derived from the U.S. Composting Council's Compost Operator Training course, which some of you may have attended in the past, but it's good background information to go over again. Now, as we know, there are a variety of ways of developing composting facilities. You can start by identifying and quantifying your feedstocks to design your facility, and then develop your markets after you've developed the facility, or you can analyze the markets and work your way backward. But we're going to talk about the part of the composting process that's inside this dashed line here. Remember that composting is a manufacturing process that's made up of several distinct steps. So we have our feedstocks that come in through the gate and occasionally across a scale. So there's a feedstock receipt function. As a part of that initial function, we have to separate out the non-compostables. And for those that can be recycled, they are recycled, and otherwise they are disposed of. We then go through a feedstock preparation step. This could include grinding green waste down to a 2-inch particle size, or it could be that we mix ingredients together in accordance with the recipe for a multi-feedstock type facility. We have our active composting stage of the process. We have our curing or maturation phase, the screening phase, which is a product preparation step, and then product storage and distribution. As part of this, we will recycle the oversized particles from the screening step back into the mixing step. Monitoring the performance of this manufacturing process is critical to good performance. And we have analyses of product. We have odor control systems for those portions of the manufacturing process that can produce odor problems. And we have dust control for other parts of the process. And equally importantly, we now have water management for stormwater runoff from our manufacturing facility. So these are all the various steps we go through to make product. We're going to concentrate on this part here, the active composting process. These are the basic methods by which you can compost organics: in piles, static piles, in turned windrows, in aerated static piles, in vessel systems, and then hybrids, which are combinations. And we'll touch on all of these. We can describe composting approaches by using these descriptor terms. They can be an open or a freestanding system. They can be enclosed. They can be covered. They can be in bins or bunkers. They can be passive aeration or forced aeration. They can be negatively aerated or positively aerated. They can be static or they can be turned. They can be a batch type system, or they can be a continuous flow type system. These are all, in other words, there are lots of different ways of making compost using a wide variety of different approaches. But the one thing that is common to all of them is this: All successful composting piles create heat. The heat is created by the microbial action in the pile, and that heat will rise just like it does in a fireplace in your home. That air that is rising out of the heated air that's rising out of the pile, that has to be replaced with cooler ambient air. So this breathing pile of microbial energy is common to all forms of composting, be it an in-vessel system or an open static pile. Static piles are the simplest way of composting and one of the oldest ways of composting. Essentially, you take your ingredients and leave them in a pile. Aeration is passive. That is to say, the air moves into the pile and up through the pile through natural convection, the process whereby heated air rises to the top, cool air replaces that heated air coming in from the side. They have advantages of being very low labor, does require a certain amount of footprint. You need, with higher organic matter and higher nitrogen, are some limitations, but you don't have much process control. It is a very slow process, can take years, and with piles that get too large, there is the risk of fire due to what is called spontaneous combustion. This is a sketch of a static pile, your basic air coming in from the side, heated air going out through the top. This particular pile shows a mulch layer at the base. This tends to act as an air plenum. We'll get into that a little bit more in a minute. And then has a covering layer that serves as a biofilter. Assisted passive aeration is a system that was developed in Canada several years ago for handling fish waste. And here what we do is we take PVC pipe or any other kind of rigid wall plastic pipe, and we drill holes in the pipe, which you can see here in this illustration on the right. These holes allow the air to come in through the open ends and up through the middle of the pile. So when you build the pile, you leave the ends of the PVC pipe exposed to the atmosphere, and this facilitates the movement of air into the pile. It can be an open pile like this one on the lower left, a pile surrounded by concrete block to make a little bunker here in the upper left, or as we see on the right, a wooden bin with passive aerated pipe inside. These are very effective if you have a highly odorous feedstock, because you're not turning them. You're just letting the feedstocks decompose and letting the air enter the system naturally. Obviously, these take a while to fully compost. The vast majority of composting facilities in the United States are turned windrow operations. And that may be true worldwide as well. It is the most common method. There are many ways of turning a windrow. The effects of turning are to restore bulk density by fluffing the pile. You do get some additional benefit of re-aeration by turning, but that re-aeration disappears rather quickly because of stimulated microbial activity. It's a very flexible system. It's easy to compost. If something doesn't go right, it's easy to start over again. It relies on passive aeration, so you have to have good, what we call structural porosity. And a structural porosity is a physical concept whereby the particles in a pile arrange themselves in a three-dimensional matrix that creates air channels for air to move through the pile. In many cases, that structural porosity is created by a hard structural item like a wood chip, or in some cases a tire chip, as opposed to a material such as straw or hay or leaves, which doesn't have that same structural rigidity of a wood chip. There are also some risk of odors with turned windrow operations. There's lots of ways of turning a pile. This is a way that many of us probably listening to this webinar have tried to do in the past, turning with a bucket on a tractor. It works just fine, but it's very time consuming and very slow. The next step up is to turn with a front end loader, which many composting facilities have that have larger buckets. This one looks like about a 6-yard bucket, where the tractor we saw on the previous slide had about a 1-yard bucket. So the more you can move in each bucket load, the better and faster it goes. Now, there's a problem with this picture, and when we teach this class at Gary and Greg's Better Compost School, I always ask the question, what's wrong with this picture? Well, the answer to what's wrong with this picture is he's driving up on the pile. So now you have the weight of a multi-ton loader pressing down on the pile. And what does that do? It compresses the pile and squeezes the free airspace out of the pile. So it's very hard, and the pile will not automatically rebound when that loader backs off. So you have lost some of your free airspace due to compression by the weight of the loader, and so you have lost some of your ability to maintain good structural porosity. Here's another picture of how many windrows are turned with an excavator. And again, the problem with this photograph is the excavator is sitting on top of the compost pile, compressing the free airspace out of it. In the lower picture, we have essentially the way it's supposed to be done with an excavator, where you approach it from the side and break down the pile from the side and rebuild it. That way you don't compress it, you don't crush it and lose your porosity. Many larger scale composting facilities, and actually some of the smaller ones, use these straddle windrow turners. This is a machine where there is a horizontal drum between the two tracks in this case, or wheels if it's got wheels, and that drum rotates. And as that drum rotates, it grabs this pile in front of it, spins it up, and lays it back down behind the machine. So it turns your windrows in place. Now, the big advantage of this type of straddle turner is the aisle you need for transit is much less. If you're trying to do this with a front end loader or with a tractor, you have to leave 15 to 20 feet between your piles for the equipment to move around. With a straddle turner, you only have to leave maybe 3 feet, just enough room for the tracks of the machine to ride along the pad. So you can put your windrows closer together. You can get more material through your facility on a smaller footprint by switching from turning with a loader or turning with a tractor to turning with a straddle turner. This is a tractor pulled straddle turner. And you see what I mean by having this large aisle, in this case about 15 feet, 18 feet. That is space that you cannot use to make products. So that's part of your manufacturing facility that is not producing revenue. These tractors have to have a gearing in the transmission that is called a creeper gear. And the reason for that is most tractors don't have a transmission that allows them to travel at less than 1 mile per hour. But to turn one of these windrows with a tractor pulled windrow turner, you must travel at less than 1 mile an hour. So the transmission has to be equipped with a creeper gear, and it generally has to be at least an 85 horsepower motor, because there's a lot of drag and force trying to pull this thing through a big pile. It takes a very powerful engine. But this is a very common way of agricultural composting because a tractor is a common farm implement that is found in most farms. We see more in Europe than we see here in the US of the trapezoidal pile configuration. This is essentially one very large pile. I believe they're more common in Europe than in the US because land area is far more precious in Europe than it is here in the US. And these piles are turned by a machine that looks like this. It travels down this side here. Literally, it was a vertical auger that shaves off about anywhere from 8 to 12 inches of the pile transfers it to the discharge conveyor, and discharges it over here. So you are literally moving your entire pile about 8 to 10 feet in a lateral direction when you turn the whole pile. So you would turn one day and move the entire pile 8 to 10 feet. The next time you turn, you would approach the pile from the reverse direction and move it 8 to 10 feet back in the other direction. And that's essentially moving it back and forth across the site. Aerated static pile is a technology developed in 1974 by the U.S. Department of Agriculture's Beltsville Agricultural Research Center, and was developed as a negative aeration system. We'll talk about that in a minute. The process was further refined in 1980 at Rutgers University, where they developed the positive method of composting with aerated static pile. We're starting to see more and more of these being built. They were originally developed in the 70s and the 80s for composting sewage sludge, because there was a program underway by EPA at that time to promote the beneficial reuse of sewage sludges, which was one of the reasons why this composting approach was developed. So over the early years of the technology, it was designed for use and meant for use with very wet, heavy kinds of feedstocks like sewage sludges, wet animal manures like dairy manure, and those kinds of materials. With the growing interest now in composting food waste, which can be, often are, a very heavy and wet material, we're seeing a resurgence in the world of aerated static pile for the purposes of composting those kinds of materials. And there are some other advantages that we'll get into here in a minute.
Craig?
Yeah.
Peter Moon from O2 Composting is on the webinar.
Excellent. Hello, Peter. Forced aeration is an active aeration approach where you are introducing air into the piles deliberately. They can be covered piles or uncovered piles. You can either blow air into the pile using basically the method developed at Rutgers. You can pull air down through the pile, which is called negative air, as the method developed by USDA. Recently, we've seen some new facilities come online. The new composting facility in 55,000 ton per year facility in Phoenix, Arizona, has a reversing air system. They have both positive and negative air. So with positive air, we have a blower or a compressor at one end, and that compressor or blower introduces air through piping into the pile, and that air conveys upward through the pile and exits. So it takes the place of the natural breathing convection that we talked about earlier by forcing air into the pile. Positive aeration systems are very simple. They tend to use less energy consumption than negative systems. Now, you do either need to have a supply of electricity at your site, or if your site is very rural, there's been a lot of success lately in solar-powered blowers for compost or ASP piles. You don't see the condensation in the piping or potential corrosion in the blower that you see with negative aeration systems, and you do get a very good distribution of oxygen. The drawbacks to positive air are you can see some large temperature gradients in the pile, where maybe the top of your pile might be at about 140, 145, and the bottom of your pile can be 110, 120, because the air is cooling the pile as it transits. As the air moves through the pile, it tends to cool the pile. So you can get cooler parts of your pile closer to your piping. There are somewhat limited options for odor control with positive aeration. We'll talk about some of them. And you do get some drying. Compost is very hard to re-wet once it's dried out to below about 35 to 38% moisture. For some reason, the material becomes very hard to wet again. Now, odor control, if you have a positively aerated system, can be done with what's called a biocover. This is basically a 6 to 8 inch layer of compost over your pile, and it should be an unscreened compost so you don't essentially choke off the pile with a compost cover. These have been shown through peer-reviewed scientific research to be very effective at removing odors. They are somewhat time-consuming to install, and if you have a kind of, for example, in the Phoenix project, they have both positive and negative air, and they turn their piles 4 times between 4 different stages. So every time you turn a pile, you have to cover it again. And with a bio cover, that can be time-consuming, and depending on how close your piles are together, can be hard to install. If you're doing all this in a building, you can capture the process air. You normally have some fairly high volumes that you have to process, plus you have to exhaust that air from the building at a frequency that allows for the pollutants that are in that air not to build up and become an employee health issue, on the order of 4 to 6 to maybe 8 air exchanges per hour. You can get fog and corrosion in a building with a positively aerated system. I worked at one in North Carolina where we would get fog problems after October 1st, and by 10 o'clock in the morning, you couldn't see your hand in front of your face inside the building. We also use permeable membranes as covers, and these are effective at odor control. They tend to be a little bit time consuming to deploy because you have to pull the covers off, put them back on, and there are several different kinds that we'll look at. On the other side, the original Beltsville Ag Research Center approach to composting was negative air. Pull your air down through the pile and then discharge it to some form of odor treatment. This was the basis for the first composting facility I worked on, which was a sludge composting facility near Silver Spring, Maryland. 400 wet ton per day sewage sludge composting with negative air and a 4-stage chemical scrubber for odor treatment. The advantage of negatively aerated static piles are that you don't have the surface odor emissions that you have with positive air, because you're not literally blowing odors out of a pile, you're sucking everything down into the pile. So you get somewhat smaller temperature gradients. You tend to keep a bit more moisture in the pile with negative air, and you have more options for odor control because you've concentrated that air stream into a manageable area. The disadvantages is that the negative aeration system is pulling heated, saturated air down through the pile. The minute that hot, saturated air exits the pile, it condenses. Even if it's a hot summer day in Arizona, it will condense and you will get a condensate that has a very low pH and could be very corrosive to the ductwork and the blowers. You do need more power because as a pile composts, the volume shrinks. As the volume shrinks, your free airspace and your structural porosity reduce. So it takes more power to pull the same amount of air through that now denser pile. You need a biofiltration unit or some other kind of odor control system. Chemical scrubbers have been used at several sewage sludge composting facilities in the past. And you do have a tendency to pull material into the aeration system. I think we're seeing today more positive aerated ASP systems than negatively aerated ASP systems. As I mentioned before, the Phoenix facility uses reversing air. This is a fairly recent development, probably in the last 5 to 10 years. You reverse from positive to negative. You have the ability to reverse what's called short circuiting. If you're blowing positive air into a pile, the pile, as the volume shrinks, as the pile decomposes, you will get cracks where air will come up through the crack, because air will always take the path of least resistance to get out. And so by going positive, then negative, then positive, then negative, you could correct some of that. Some of the other advantages and disadvantages you see here: it does require a lot more dampers and ducting and blowers And you need both a biocover for positive aeration odor control and a biofiltration or scrubbing system for negative air emissions control. This is how the aeration piping is laid out. It's basically, here we have a positive aeration system. We see the opening here on the side of the fan is the suction side. This is the discharge side of the fan. This transitions into a manifold, which is used to distribute the air through the distribution piping. Some composters will take another piece of aeration manifold and put it down at this far end over here and basically create a closed loop system. One drawback to this approach is the suction side here gets close to the ground, so in many cases you will want to have some sort of an inlet filter to keep dust and dirt from getting into that blower and causing accelerated wear. This is a negatively aerated system, extended aerated static pile. It used to be in Philadelphia, right along Interstate 95. It was for composting sewage sludge. And I was at a meeting in Pennsylvania a couple of weeks ago, and the city is looking at this site to do food waste composting on it now. Aerated bins are very popular in a lot of smaller institutional settings like schools and universities. This was originally developed as an alternative to on-farm static pile composting. And so there are a few technology producers in the country that provide these aerated compost bins. And here we see most of the aeration system is on the side of the building, and the aeration piping will serve more than one bin. So with traditional aerated static pile, you had one blower per pile. With these kinds of aerated bin systems, sometimes you'll see a blower handling 2, 3, or maybe 4 bins, depending on size. They tend to be a bit smaller in capacity, again, because the technology is meant for and developed for on-farm applications for manures, mortalities. It's meant for institutional applications for prisons. There's a prison in Philadelphia using an O2 compost system. There's a University of North Carolina using an advanced composting technology system. There's quite a few of them around now. These are the kinds of enclosures that we see used in compost aerated static pile. On the upper left, we see reinforced concrete, often used to create the walls. So each one of these bunkers is a fixed volume. I normally size them so they can be filled in 2 days, 3 at the most. The advantage of reinforced concrete, you see in the upper right, you can hang all your electrics and your piping and everything on the back wall behind the facility, behind the compost bunker. In the lower picture, we see these reinforced concrete blocks. These are generally tongue and groove. You can see right there in the image, the groove and the tongue at the top of the block. So they fit together like Legos. And you can make very nice bunker walls using these kinds of concrete blocks. Piping is either PVC or HDPE. On the left picture, we see the kind of ABS drain pipe that you might see for sale in a big box hardware store that is used to divert rainwater away from your house from the downspout. In the early days, we used to use a lot of this, but the problem with this cheaper piping is that it's very fragile and gets destroyed during the process, and you end up replacing it all the time. The soft wall HDPE tends to deform a little bit under the heat of the pile and tend to produce an oval as opposed to the round shape, but they work very well. PVC, of course, is rigid and somewhat brittle, and the exposure to both sunlight and to the heat of the pile tends to make PVC a little bit more brittle. Now notice that the aeration pattern in a positively aerated system, because you're closer to the blower at this end of the pipe, more air comes out here than comes out way down here because of frictional losses in the pipe. Some composters will vary the hole size, making the holes in the pipe bigger down here and smaller up here to try to balance that airflow out a little bit. This is an interior view of a biosolids composting facility that's using in-floor, what are called spargers, in-floor spargers. And the design team decided to deal with the change in pressure loss by changing the hole size. So closer to the blower, they had 3 openings. Further away, they had 5 larger ones. One big drawback to these kinds of aeration systems is they are very easy to clog up. And aeration floors are the key to a successful aerated static pile. You have to be able to deliver this air efficiently and effectively throughout the decomposition process. So you have to be able to deliver the most amount of air when your decomposition demand for oxygen is the highest, but also keep enough air in order to keep the pile temperatures constant and cooled. In the upper left, we see a traditional rectangular concrete trench. This is formed by building essentially a box in the formwork and then pulling the box out as the concrete sets. We have the spargers that we saw on the previous slide here on the upper right. On the lower left is a method I used at one of my facilities by taking angle iron and turning it around upside down to create a V-notch. Which you see here in the concrete, and the V-notch carries the pipe. This is one I built for a pilot test out of timber, where the timbers were chamfered for the pipe to stay below the surface. And the reason you keep your piping below the surface is so that you don't damage it with your loader bucket when you're emptying or filling a bin. So lots of different ways of delivering aeration through the floor. Whichever method you choose will depend on a combination of budget and similar constraints. One common problem with all aeration systems is they have to be maintained. We see here at the red arrow, the aeration channel will get packed with compost, and I have personally spent many hours with a pickaxe and a broom trying to get that stuff out of aeration channels. It's just a never-ending headache with aerated static pile systems, either negative or positive. Okay, we're going to switch. We have, as I think was mentioned early on, we have some poll questions in our presentation today to see if everybody's been paying attention. So here's today's first quiz. We have 2. This is our first quiz. And when after I read the quiz, Mark is going to put a poll up on the screen that you can respond to. The question is that there is an advantage of forced aeration where you're blowing air into a pile or sucking it down through a pile, the advantage over a passive or a convective aeration system. One of these answers is correct, the others are not. Does the forced aeration system save money on electricity? Does it mean that you need less bulking agent in your mix? Does it mean you can process more tonnage of feedstock on a smaller footprint? Or does it mean you need less water for moisture control? And we'll let people answer the questions you see on the screen.
Yeah, folks, I've already started answering. We'll just take another 20 seconds maybe. Getting some good answers in. It's not weighted. It's not all the same response. So it'll be interesting to see what y'all have to say. Just another 10 seconds and we'll end the poll. Alrighty. I'm going to end this now and then I'm going to share the results. Craig, are you able to see those?
I am.
Okay, good.
And the majority of people did get the answer correct. You can process more tonnage on a smaller footprint. That is correct. Okay, moving along then. Now, aeration floors are designed based on providing airflow uniformity, as I mentioned before. your pipe spacing laterally under the pile should be less than 2/3 of the height of the pile. So if in the image you see here on the upper right, a 9-foot tall pile, you would want your pipes no more than 6 feet apart. In some of the earlier photographs I showed where I was using the angle iron for smaller diameter piping, in those systems I was using 1.5 PVC and I was putting it at 12 inches on center. So these larger type spacings are more appropriate for the traditional PVC piping of 4-inch diameter piping. You need to make sure that the airflow, that the aeration system and the floor delivery system can meet your peak aeration demand. And the table you see here is provided by one of the technology providers in the world of aerated static pile composting, who believes that in the first 10 days you have your highest aeration demand, which of course you do, because that's when all the decomposition is occurring. And then over time, as the organics decompose and the compost process begins to wind down, that airflow rate demand decreases. You also need leachate management. These aeration pipes will fill up with water. Under negative aeration, of course, it's a significant issue because of the condensate. You even see it in positive aeration. If a pile's a little bit too wet, when it's mixed up, the free water will drain down into your piping. And what we've seen with food waste is that with food waste piles, as the heat builds up from microbial actions, the heat tends to break open the plant cell walls. And as we know, fruits and vegetables are largely water. And when those plant cell walls break open, there's all that water that's inside that plant cell comes out. So there's a little bit of a flush of water in day 2 or day 3 or day 4 of a food waste pile. So you want to have at least some way of draining your pipes to get that leachate out. Okay, we're going to do I'm going to walk you through a math exercise and on how to calculate what size blower do you need for a pile. Now, as we talked about earlier, peak aeration rates are given in cubic feet per minute per cubic yard. That's one technology vendor's approach to it. Or the engineering approach from the book called Compost Engineering by Roger T. Haug, which I strongly recommend for all your libraries. Tim's a good friend of mine, and it's a brilliant book on compost engineering. He uses cubic feet per hour per dry ton. So let's assume our compost facility has aerated static piles that are 8 feet tall, 8 feet high, they're 18 feet wide, and they're 44 feet long. We'll assume each pile holds 106 wet tons of material, and that moisture content at the end of the active composting stage is 45%. We'll assume peak aeration rates of 750 cubic feet per hour per dry ton, CFH per DT, or 3 cubic feet per minute per cubic yard. So what size blower are we going to need? Okay, for the first approach using Tim Haug's method, we have 106 wet tons at 45% moisture. That means we have 45 dry tons of material in that pile. If we have 48 dry tons of material at 750 cubic feet per hour per dry ton, we need 35,640 cubic feet per hour to meet the oxygen demand. We divide 35,640 by 60 minutes in an hour, or we need 594 cubic feet per minute of airflow into that pile. Okay, the other way to solve this problem is using the technology vendor's approach of airflow per volume of pile. We have a pile that's 8 by 18 by 44, 6,336 cubic feet in the pile. As we all know, there's 27 cubic feet in a cubic yard, so we have 234.7 cubic yards in our pile. We're going to aerate that pile at the rate of 3 cubic feet per minute per cubic yard, or we'll need 704 cubic feet per minute. So with one method, we've calculated we need about 600 CFM, with the other 700 CFM. I always recommend going with a larger estimate, because the way my approach is, you can never have too much oxygen. So just a quick math exercise on how you calculate how big your blower is. When you have positively aerated systems in a building, you have to divert the building air to a biofilter, as we talked about a minute ago, and this is some examples of how that's done. This is a facility I designed in North Carolina. This building is 450 feet long. It's 250 feet wide, 30 feet to the eave, 45 feet to the ridge. These are exhaust pipes that are mounted high in the wall on the inside. They pull the air out of the building through this suction blower right here. So the suction side of the blower is set up to suck the air out of the building. It then discharges on the discharge side of the blower to these pipes, and they transition to these manifold distribution pipes. And then this is the biofilter bed. So the biofilter bed is 450 feet long by 100 feet wide by 4 feet deep. And this building exhausts the building air at 6 air exchanges per hour, and even that wasn't enough to keep the fog from building up on the inside. But that's one way of exhausting the building air to a biofilter. With negatively aerated systems, as we've talked about, you have the flow coming down. You've got to have the biofilter or some other form of treatment. This is the one in Howard County, Maryland, which some of you may have seen. The aeration piping is here. It sucks up into this manifold, and then down that manifold, the biofilter's at the far end of this run of pipe. This is the negatively aerated pile at Washington State University. Again, a negative aeration system manifold here, and treatment. So these are all, the minute the hot air hits this black part right here, it condenses. So you've got a condensate issue that you have to manage with these kinds of systems. Now, biofiltration is a process that we use for odor management, not only in composting, but we see them used, for example, for odors from sewage pumping stations. I've seen them used for solid waste facilities like transfer stations. There's a number of different applications of biofiltration. The process works very similarly to a compost pile. As we see in the upper right-hand illustration, this is our classic compost pile. We have air flowing between the particles. We have microbes living in a thin layer of moisture around each particle called a biofilm. And the oxygen transfer across that biofilm is what gives the microbes the oxygen they need to breathe. Well, we have the same process going on in a biofilter. The organic compounds are absorbed into this aqueous layer, this biofilm around each particle, and are absorbed onto the media surface. The microbes then degrade. By biodegrading those odors, they reduce them. The media that is used to support the microbes is usually a mix of compost and mulch. And so the exhaust gases pass through the biofilter media. We design these for what's called a gas retention time. In other words, the exhaust gases stay in the biofilter for a finite period of time, usually 45 seconds to 1 minute. And that biodegrades the material. It doesn't, for indoor facilities where you have a lot of diesel equipment running around inside the building and you have carbon monoxide emissions from the engine exhaust, you probably need a longer biofiltration on gas residence time to biodegrade the CO. This is a cross-section of one. Basically, you put it on a slope so the moisture can drain to a drain point where you can collect it. You put it in a bed of gravel. This gravel bed acts as a as an air plenum to help distribute the air more evenly throughout the biofilter. And then you have your 4-foot thick layer of mulch and compost to degrade the airstream. Now, we talked a little bit earlier about covers for aerated static pile and also for windrow systems. We're seeing more and more covered composting systems. We have what are called porous covers. Compost Tex is the brand name. These tend to be polyethylene fleece type covers. Micro-porous is a particular chemical configuration that is used to make Gore-Tex fabric for Gore-Tex windbreakers. That's offered by a couple of producers. And we have impermeable covers that have air holes in them of one form or another. So here we see the polyethylene fleece cover. You see the roll-up, the wind-up roll here. So as the system is set up so that as he traverses down the long axis of the windrow turning it, his take-up reel will wind the cover up on the reel. He can turn the windrow and then unspool the cover back over the pile. This is the Gore micro-porous fabric. This is a very low micron mesh. It barely emits, just size to emit water vapor and nothing else. What happens is odors are trapped in the layer of, there's a layer of moisture that builds up on the underside of the fabric. Odors are absorbed into that moisture layer and drips back into the pile to help control odors. And these are anchored down with weights. This is the negative aerated static pile system. These have very small aeration holes in them to allow the air through into the pile. These are basically a modification of the old farm-based method of making silage, where you put the hay in a plastic bag and let it ferment. This was developed many years ago for composting and has fallen out of favor a little bit because it's very difficult to keep the bottom of these bags from having excessive amounts of moisture in there. So different ways of covering or making piles impermeable as well. And then the other major approach to composting, of course, is in vessel. This covers a very wide range of technologies. The significant advantage is you have some more control than you have over static pile, turn windrow, or even aerated static pile. And of course, because everything's contained, you minimize the impact of weather. The disadvantages are that they tend to be expensive because they are complicated electromechanical systems and they take a fair degree of management to do properly. Here's one that was developed many years ago for sewage sludge, and we've seen it, haven't really seen this migrate too much into the world of yard waste or food waste here in the US. I run across a lot of these overseas for doing the organics that are coming out of mixed waste materials recovery facilities. In this is an agitated bed system. We have an aeration aeration system in the floor, so it's a positively aerated system. At the same time, we have a machine that rides on top of these concrete walls. You see it right here. And it has an agitator that extends down into the pile and turns. So the machine comes down the aisle, turning as it goes, and literally pushes 10 feet, 8 to 10 feet of the entire channel gets pushed out by the agitator, opening up 8 to 10 feet back at this end to fill with fresh material. We've seen a wide number of bins and boxes used for controlling, for composting. These earth tubs are popular in small schools and university settings. Nature Tech has a system of bins. Hot Rod is a New Zealand company. These are horizontal bioreactors. There's a shaft here, an auger shaft in this machine that turns and moves the material through the first system, and then up the auger, and then into the second system. Two technology providers that make batch systems that are modified shipping containers, basically, GMT and Green Mountain Technologies and Engineered Compost Systems. These are batch operations. You fill the box, close the door, turn the fan on. Rotating drums, originally developed as a way of processing sewage sludge to meet the federal requirement for process to further reduce pathogens in 3 days as opposed to 15 days. This is an American provider, B&W, out of Texas. You see these used in many cases on mortalities from poultry farms. This is a Japanese unit called Odor. But again, big electromechanical systems. In the U.S., some of these have been used for pre-composting MSW, which is municipal solid waste. Bedminster Bioconversion was the company that developed those many years ago, and there's still 10 or 12 of those operating in the U.S. They take solid waste right out of the trash truck and pre-compost it before they sort out the recyclables. These are tunnel reactors. These are very common in Europe and in Canada. We're beginning to see a few of them here in the U.S. These are essentially long rectangular boxes with an aeration floor. You fill the box with a front end loader, close the door, turn the fan on. Again, they operate in batch mode, 21 to 28 day residence time in the box. This is the Inland Empire Utility Authority in California, which converted it a old IKEA product distribution warehouse. They converted this to a positive extended aerated static pile system inside the building. This is their curing building back here under the fabric building, and then their biofilter is here beside the building. And of course, their neighbors are wastewater treatment plants, so I don't think they have too much of an issue about odors. We also see many hybrids used now, and hybrids consist of different approaches for composting followed by curing. So we can go with the in-vessel system to aerated static pile second stage to passive pile for curing, or we can go, this is commonly used, aerated static pile composting followed by turned windrow curing, or some other combination. So again, we have these descriptive factors that describe the different approaches and systems in composting. Open and closed, covered versus contained, bins versus in vessel, passively aerated versus forced aerated, negative, positive, static, turned, batch, and continuous. Lots of different ways of making the product we all call compost. What technology you select for your facility really is dependent on several of these factors here. What is the competing landfill gate fee? You know, where I live in Virginia, the average tip fee is probably around $28 to $30 a ton. Very hard to compete with that solid waste disposal fee. Land prices, obviously land prices greatly influence technology. If you're anywhere in, say, near a major metropolitan area and land prices are typical of those kinds of urbanizing environments, you're probably not going to be going with a turn windrow system where you're using a tractor pulled turner, because you're going to need a lot more land, and land is expensive. Tolerance to odors. If you have sensitive receptors, and by that I define a sensitive receptor as anywhere where the public gathers, church, park, shopping center, school, hospital, whatever. If your sensitive receptors are within about 1,000 feet, you're probably not going to go with a technology that has a higher risk of odors. Transportation cost is, of course, the distance between you and your waste source and the distance between you and your market. The value of compost, some markets have very low compost market values, so you can't spend a lot of money on technology if you can't get a good price for the material. Feedstock quality, if you're dealing with a wet, heavy material like a manure or a sludge, you're going to need more technology than you might otherwise would say just green waste or yard waste. And the availability of bulking agents. If you've got competing carbon demand in your area, for example, where I live in Virginia, we have 2 power plants that run on biomass. We have 3 paper mills. We have 2 engineered wood products plants, and those create a huge demand for wood chips. So it's hard to find wood chips in this part of Virginia. And that's the case in some other areas as well. All right, let's take another poll question. This is an easy one. We've been talking about in-vessel composting systems. So the question is, which of these is not an in-vessel composting system? A horizontal bioreactor, B, a rotary drum, C, positive forced aerated static pile in a concrete bunker, or D, tunnel reactor.
Okay, folks, polls launched and a few of you have responded. Let's just take another 20 seconds. Okay, just another 10 seconds. Okay, so I think most folks probably got this one right, although there are a few that chose tunnel reactor.
Very good. Most of them got it right. And that concludes our my part of the webinar series for today. This is my contact information. Feel free to reach out either by phone or by email if you have any questions about the wonderful world of composting. I'm always happy to help. And with that, I will turn it back to Gary and to Mark.
If we have any questions, please put them in the QA box. Craig, on the very last thing, could you tell one point that really decides whether it's an in-vessel composting system or not?
One point, you mean one characteristic or aspect?
Yeah, there's one characteristic that's pretty important about in-vessel systems. It doesn't get rain.
Beg your pardon?
It doesn't get rain on it.
Well, that is true. They are weather resistant.
We don't have anything in the Q&A. We have a webinar coming up about a month from now. Here's a question. Oh my, I got 2 questions. Okay, one of them is a process question. I'll save that for a moment later. That one will be one for Mark to answer. The question we have is, when selecting a blower size, how much do you consider back pressure as a function of mix density? Did you get that, Craig?
I did. You want me to take to respond?
Yes, please.
In most air blower design systems, you assume a pile static pressure of about 6 inches of water. Pile back pressure varies based on mix quality, based on time, because piles shrink and compress over time, based on size of bulking agent, lots of different things that influence it. So I have found that with the ones I've designed, if I start out with assuming my blower is going to have to meet my demand, if you look at what's called a fan curve relates the blower horsepower to the CFM of the air discharge to the static pressure of the pile it's trying to blow into. And you want to size that fan so you get your desired air delivery rate, however many cubic feet per minute you need, based on a 6-inch water pressure. And that then translates into how many horsepower you need. I've used it several times, tends to be a fairly reliable unit of measure.
Does that fully answer the question?
Yeah, whoever asked that, if you want to add something to chat, click clarify or add it to Q&A. We'll be glad to follow up. On the question someone asked about watching the previous classes, so let's do it this way. I mean, there's a couple of ways to do it, just like everything else in tech, right? I'll put a link in chat. So this is to today's event. Someone also asked about the slides. There's a link. If you scroll down on this page, there's a link toward the end that has the slides there. If you look on the related events, you can actually see the upcoming webinars there on this same page. Probably the best way to view, well, so another way to view the entire series is there's an event materials link at the bottom of this page that says download series webinar schedule, which has a PDF in it. That has links to learn.extension.org for all of the webinars for the upcoming ones, including the ones in the past that we've done. So that's sort of a roundabout way of saying it. You can also search, if you know the name of the webinar you're looking for, you can also search for that inside learn.extension.org.
I think we've covered everything. Oh, here we go. Is there a recommended way to calculate the volume of an ASP? Craig, you did a calculation, and I think what you did was a trapezoidal shape.
Yeah, no, and it's essentially a prism. It depends on the nature of the ASP. For example, if you're building one in a concrete block bunker with a rectilinear walls, then you have a rectilinear, essentially a three-dimensional rectangle up to a certain point, and then you have the essentially the exact term is escaping me. But from about...
It's a parabola.
Well, no, the front part of it is the angle of repose. That's it.
Oh, okay.
The angle of repose of the face of the pile, if you don't have, say, a series of boards or some sort of gating system to make it a complete rectangular, three-dimensional rectangle, the first part of your pile is going to slope backward by the angle of repose. And then you start your rectangular pile. So you end up with a three-dimensional triangle attached to a three-dimensional rectangle. If it's an open air pile, it's really a trapezoid, three-dimensional trapezoid, because the top of the pile will always be narrower than the base, both front and back and on the sides. So it really depends on the nature of how you build your pile.
So let me jump in here a second. This is Greg Vanilo. I'm one of the developers of this series, and there are publications that will provide the equations for calculating the volume of windrows of about every conceivable shape. I think that's something we could probably identify some URLs for that and share. Perhaps we can put a link to this, to Craig's presentation today at the bottom of the page. I'll do that within the next week or so. And also, just while I do have the mic, to let you know that in about a month, September 18th, September 15th, there will be our fourth webinar in the series, and we'll again be hearing from Craig on this one, and it's going to be site selection and design.
And I'm putting a link to that in chat. And then also, if you notice the 1 and 2, someone asked about the previous webinars, there's links for 1 and 2 there also. And Gary, there's a couple more questions in Q&A.
Yep, I'm answering one offline right
Gotcha.
now. Well, thank you, Peter. How many people attended the webinar? We had somewhere in the neighborhood of 40 most of the time. It's varied from minute to minute. And from Maria Carolina Capistrini, she said thank you to Craig and to Greg. And those are the questions.
So do we have I suppose that there was no final evaluation developed for this one. I didn't follow. I don't think I followed up with that. We had them only for the previous ones, so we'll have to just assume that Craig did his great job.
Well, I learned something, so that's been a good one for me. Mark, I think we're ready to sign off.
We're good. Okay. Thanks again, everyone, for their time, and we hope to see you back here again next month.
Thank you, everyone.
Thanks. Bye-bye.